Well, hello class. Oh, good gracious, I think I'm speaking to an alien. There's a little green man in here with me. How truly bizarre. Well, Unit 2, Lesson 2 is about nonlinear initial value problems. Remember what it means to be nonlinear? Something might appear to a power or is composite in some other function or something like that. So I seem to be speaking to some aliens here for some reason. Oh, well, this one wants me to take me to my looter, but I guess I'll have to do that after this lesson's over. So, one example of this type is a logistic equation that we've seen before. And recall that an important model for growth or decay of a population is dp dt, the change in the population over time, is proportional to the population equals k times p, with k either the growth or decay rate. But in reality, the growth rate will slow over time due to some limiting factors, such as space available, the availability of a food source, shelter, diseases from overcrowding, etc. So we can expect k, which equals dp over p, to decrease as p increases. In other words, the growth rate is a decreasing function of p, the population. So this is some decreasing function of p. Here it is. That is the decreasing function of p. And so we'll write that f of p equals dp dt over p. Or maybe write it another way, dp dt equals p times some decreasing function of the population. So if we further assume that the decreasing function is linear, so it would look like this: f of p equals mp plus b, slope-intercept form. But since it's decreasing, we'll say it's f of p equals b minus m times p for 0b to y-intercept and the slope a positive number, so it would be negative within this equation. So we've got change in population with respect to time is a product of the population and a constant b minus a constant times the population. So that is called the logistics equation, and the solution is called the logistics function, but we can actually solve it as a separable equation, although it was solved as a Bernoulli equation in Unit 1, Lesson 8. But we'll solve it here as a separable equation because when you want to solve this, just make all the p's on one side and the t's on the other, and you just get dp over p times m minus, or b minus m times p equals dt. The right hand side is just t plus c. That's not a problem. The left hand side we can do by partial fractions. A over p plus b over m minus bp equals 1 over, that's the coefficient here in the numerator, 1 over p times b minus mp. So we've got the fact, if we multiply by this denominator on both sides, we've got the fact that a times small b minus mp plus capital B times p is equal to 1. So that means a times b is equal to 1, or a equals 1 over b. And by the way, you can also see that bp minus amp equals 0, so b minus m over b equals 0, therefore b equals m over b. Do you see that? B would be equal to m over b, because remember a is 1 over b. So that's b minus m times 1 over b equals 0. See, you factor the p out of that, so then you figure what remains must be 0. So I hope you can follow that all right. And the integral is the integral of a over p plus b over b minus mp. Remember, this is the b that we found here. And so that would be 1 over b times the ln of p minus 1 over b, that's this b, times the ln of b minus mp. Notice that the m, when we let u equal b minus mp, and the m here in the numerator canceled each other out. So simplifying this now is actually not too bad, since I got this 1 over b as a power here. So it's 1 over b times the ln of p divided by b minus mp And 1 over b times that is equal to t plus c. Remember, that was the right-hand side when we integrated this. So now, multiply both sides by b, and we got rid of this fraction. So that way we have ln of p over b minus np equals bt plus c. It's actually c times the other b, but it's an arbitrary constant, so we'll just call it c again. Making both sides exponents for e, we have p over b minus m times p. That's an absolute value equals c times e to the bt. This c is e to this c, which was b times this c originally, but it's still arbitrary, and that'll get rid of our absolute value sign. So multiplying by this denominator, we got p equals c times e to the bt times b minus m times p, and clipping all the terms on one side that are like, because we multiply this out, we got c e to the bt times negative mp. We'll add mp times c e to the bt to both sides, and we have it on this side now. Plus p equals c e to the bt times this b. See it? Of course, this is arbitrary again. This times this is arbitrary again. But we can factor a p out of the left side. See? And then we can divide by this, the expression I've highlighted there. And so we get p equals c times b times e to the bt divided by c times e to the bt times m plus 1. Okay, that's dividing by all of this. You know what? I'm not telling you what I'm dividing by because there's something else that's in that divisor. Plus 1. There we go. So we divide by this whole thing right here. And now, simplifying further, we get this more convenient form. Now, how do we get this convenient form? Well, you could probably see it. We're going to divide by e to the bt times c times m. So we get this b over m in the numerator, and this becomes 1. That's our divisor, see? So when we divide that by itself, we get a 1. And then this divided by this thing is 1 over c e to the bt times m. But remember, this c times m is just an arbitrary constant also, so I'll call it c prime this time, times e to the negative bt. So there it is. There is our logistic function, but we can still simplify further. And note that the limit as t goes towards infinity of this, well, e to the negative infinity is going to be going to 0. So we'd have b over m is what the population is growing to after a long period of time. Sometimes that number b over m is called the carrying capacity, k. And if we do that, then the y-intercept is 0, k over 1 plus c. Think about that. You know, if this is 0, we got that k over 1 plus c. And we also have the carrying capacity in the numerator. So here's the typical format you'll see this in. Population is k divided by 1 plus c times e to the negative b, t. And the y-intercept, of course. So we need one more bit of data, and that's another initial condition, whatever it may be, to find our value of b. But that was a lot of parameters in there. And so now we're down to just needing one thing to find the value of b. Interesting that the y-intercept over the slope is actually the limiting value of the population. That is the y-intercept and the slope of that decreasing linear function that represents the changing growth rate.
Unbelievable!
Believe it.